Hello there. Welcome to a brand new season. So I'm going to start from the very beginning. We're going to go through the mechanics, and then electricity and magnetism, and then modern physics and optics will come later. So there will be a whole bunch of episodes for this season. So today we're going to start with the most fundamental thing we need to cover. That's vectors. So when you have a vector, unless you have a very good understanding of vector, it's very difficult to actually do things correctly in physics. So vectors are basically a mathematical quantity, and there are lots of physical properties. They obey the mathematical properties of vectors. So we call them vectors. They have a vector-like property. Like momentum is a vector property. Energy is not a vector property. Electric field has a vector is like vector, is a vector. Force is a vector. Velocity is a vector. Acceleration is a vector. Displacement is a vector. A whole bunch of things. Temperature is not a vector. So there are properties which are they obey the mathematical rules of vectors, and there are properties which obey rules of just a scalar or maybe even more complicated quantities like matrices and things like that. Okay, but we're just working with vectors, and there are basically three ways people look at vectors. One is like extreme abstract mathematics way, which is called axiomatic, and we're not going to do it. When you study quantum mechanics, you really have to learn the more advanced way vectors should be looked at. But for introductory things, the most important one is graphical or pictorial or geometric. It's a geometric way of looking at things. Another calculational way is called analytic, and we'll do both of them. We'll just do today we're going to do geometric. So today will be geometric. Also graphical, we just say just kind of drawing pictures and things like that. So all vector quantities have so vector quantities have two things. Vector quantities have two things, all of them. One is, you can say how big it is, the magnitude or the length have a magnitude. So we call it a magnitude, how strong the vector is, like how strong the force is, how fast something is moving, So magnitude, or sometimes just called length. Even the magnitude of the force vector is a length of the force vector. It's not necessarily length as like 5 centimeter or 10 centimeter. It's not that length, it's length of the vector. So it's kind of loose language. Or when you represent a vector by graphical way, you draw an arrow. So basically, what's the size of that arrow? That's the length. That will represent that vector. So if I have a force vector, and we draw, say this is a 2 Newton force. So we say this much is 1 Newton and this much is, so this much is 1 Newton and this much is another Newton. So we draw 2 Newton size of that. So the length of this will be what we mean by the magnitude. And then there is the force is acting in that direction. So the other thing you need to do is direction. And it's the direction part that actually makes it difficult mathematically. Okay, so we will call this like an arrow, not all the numbers, etc. So we can try and write everything. We will just draw we say there's a scale is this much, this size, like this size is 1 Newton, and we can draw, this is 2 Newton force, and we can draw a 2 Newton force in that direction. So use the same scale. So this is 2 Newton force in that direction, and you can draw 2 Newton force over here, same direction as that, same, so there's the same length. Now this force, if you call this A, and this force you call it B, then even if you're drawn two different places, but they're same direction and same magnitude, then these two forces are equal to each other. So I can draw same force anywhere. So suppose you had a bar and you're pushing it over here, you're pushing it up over here with a, say, 1, 2, 3 Newton force. Okay, so this is some, say, F some force here. Now this force by itself, I could, although it's happening over here, I could draw over here. As long as I keep the same length, it's going to represent the same force. So the force can be moved around in your diagram. Although conceptually you must maintain it, for rotation, other properties you want to discuss where the force is acting. But for overall motion, you will see that you can move the vectors around, and that's okay. All right. So that's what vector quantities looks like graphically. Okay. Okay. So now that you have a, say, you have a vector this, and so this is some vector A, and we've chosen a scale here in whatever quantity it is, and I want to say two times this vector. Well, we'll use the same scale, we'll keep the same magnitude, so this will be 2 times A vector, because I made the length the same length and same direction, not same length, same direction, twice, 2 times magnitude. So you can call this as a B vectors. So you can see the B vector is actually 2 times A vector. So we want to be able to do that. What we say is a vector can be multiplied by a scalar. So this thing will say a vector can be multiplied by a scalar. Vector can be multiplied by a scalar. So this scalar is a positive number that keeps the direction same. Now if I multiply by -2, so it's going to be exactly opposite and twice the size of this, so this will be -2 times A. So this can be you can call this vector C. So C here will be -2 times vector A, and sometimes people just say -2 like this, just to emphasize multiplying it here. If I don't have anything there, that means actually I'm multiplying by a scalar. So this is a multiply by a scalar. So another have this, and third property can multiply by a scalar. Multiplied by a scalar. And this positive scalar means same direction. Negative scalar will mean reverse direction. That's the result. Okay. So what else we require? What else we require? Well, we require that two vectors can be added to give a third vector. Addition. So how do we say we have two vectors? We have, say, vector A, and then there's a vector 2 times A. It's the same direction but twice as big. When I add them, how do I add them? We just place this vector. Remember, I can move the vectors around for doing the algebra. So this will be our vector A, and then on top of that that's 2A. So from here to here, the result is this is a B. So this is C. C will have 1A plus 2A, so C will be 3A. Basically what happened was A added to the B and gave me 3 times A, same direction. Well, what happened if I do A but add minus 2A to it? Well, you'll see what happens. So this will be, I do the same thing. I draw A, go to the tip and draw this guy at the end of the tip. So the result is I started here, I ended here. So that's the answer. So this is the B equals to minus 2A, and you can see this is minus A, which is the C. So again, C equals to A plus minus 2A equals minus A. So I get a reverse vector. So it's for, as long as it's acting along the same line. This adds vectors. This, by doing this, you can say this subtracts vectors. What if they're not in the same line? So if I do A and I want to add B to it, how do I go about it? I'll go exactly the same way. I will draw A. I can displace or draw it over here, and I go to the end of that and draw B from there. So like this same direction. So from I was start here, end with here. That's what the sum will be. Sum vector. So sum vector is from the beginning of the A to the end of B, B having drawn from the tip of A. Sum is just A plus B. Now you can see very interesting thing here, that had I drawn B first, so I had drawn say B first, it will come out like this, and then drawn the A, I would end up the same way. So this will be the same as if you draw B first and A later. And this sum is just going along the diagonal. So A and B are the sides of a parallelogram, and sum is the diagonal. So when you add two vectors, when you add A and B, the result is a new vector that is diagonal to the diagonal of the parallelogram drawn in this manner. You start from some place, you draw the first vector, and then go to the tip and draw the second vector along the same direction as the vector is. Vector used to be here, but I redraw it over here. Just like vector A used to be here, I redraw the vector over here. And the diagonal will be the direction from the starting to the finish. Okay, let's draw some interesting vectors problems and to make use of these. Okay, so the vectors add we say that the vector size by drawing that parallelogram. So you draw vector A, vector B, and then you complete the parallelogram, and the diagonal is where the sum is, and that's the direction, and the magnitude will be according to the scale of A and B. Now when you want to add A to B, they both have to be the same kind of vectors. Like if A is velocity vector, this has to be also velocity. You cannot say, oh, I add velocity here and on this side I add force. No, you can't do that. You have to add same type of property. Okay, so let's draw a diagram where you add three vectors. So you have A, and so I want to add A plus B plus C. What will I get? Well, I'll go to the end, I will draw the B, say the B was in this direction and it was that big, and then I will draw C, maybe C was that, so I ended up here, I started here, so this will be the vector, that's the sum of these things will be that vector. Now suppose we are vector which, when I do this, it forms a triangle. So A is like this, B is like this, and we draw C, it just comes right back to where it started. Now this is a very special situation. We started here and we ended the same place, right? We started here and in the same place. So let's call this point P. So now if you draw P to P, you have a zero size vector. So P back to P is a zero size vector, zero magnitude vector. So we can just have 0 with an arrow written like that. So this will be A plus B plus C. You add up A plus B plus C is equal to 0 vector. So now if I take a C on the other side, I get A plus B equal to 0 minus C vector. And of course, 0 vector, you add any vector, you can get the same vector back. So 0 vector is a very special vector. So any vector B plus 0 vector, you should get a vector, same vector out. So this is just nothing but the reverse direction of C. So now you can see that you can see if in this diagram the log parallelogram actually worked out. And let me try to show you it works. Okay, so if I add A and B, see what I get. Okay, so A is that way and the B was that way. So their sum, because I start from here, go there, and from there I draw the B, I ended over here, so that should be the answer. So this is A plus B should be this vector. Now you look at this vector and this vector, they're opposite of each other. So this is equal to reverse of C, which is equal to minus C, and which is what this gave us. So yeah, so as long as you add vectors in a log parallelogram, you are going to get the correct way to add the vectors. Okay, let me do one more. Okay, so I have all this a diagram in which the vectors are just drawn without regard to whether you want to add them or not, and we want to be able to tell what the relationships is that. So if you look at this and say I start from that point P and go around, I'll come back. So I go here, it's fine. So I got A. but this is opposite, so I'm going to invert that to make it minus b. So that's minus b. I have to add minus b, and then I'm keep going in the same direction. C is okay. Then I'm going the opposite direction, so the d will be minus d, and then I go the e in the same direction. That's a plus e, and then I'm going the same direction as f, plus f, and that's p back to p. This whole thing is a zero vector. Sometimes when you write zero vector, people just write zero and they don't put an arrow over the symbol. But it is a vector because it's a vector equation, so it's okay to keep a good habit. Okay, so this is how you get what is called a vector equation. And this diagram that we had is a diagram that represents this equation. Okay. In applications of vector, which are defined based on these things that this is enough to define vector. Their application actually involves some more concepts and some more properties of vectors. So sometimes we like to know how much of a vector is along certain direction. So direction is a direction of another vector, right? So we have a property which is called projection of one vector, projection of a vector A, of a vector in the direction of the other vector, in the line of action of another vector. So let's see, what is line of action? Line of action is, so if I have a vector, A, draw like this extend back and forth, this is the line of action. Okay, so let's see, suppose we have a vector A this way, and there is a vector B that way. So I want to say projection of B on A. How do I define projection of B on A? So we want to know projection of B on A. So what we'll do is draw both vectors from coming from. So I'm going to translate this, go all the way here, draw in the same direction. So common point drawn from the common point. And this is important. Sometimes people just don't do this and they get pretty confused. You draw it from the same point. And then I'm going to do from the tip of this, on the line of A, I am going to draw a 90-degree line. This is 90-degree line. When it hits that line. So let's call this common point P. So this length, we call it projection of B on A. It's called the projection of B on A. And clearly, if I could have a projection of A and B. Now this is not to be confused with projection of A on B. They're two different things. So projection of which vector upon which vector is very important in our consideration. Okay. I'll show you why that's different. Let me clean a little bit. Okay. Suppose I want to do projection of A on B. Now they're drawn from the common point, so this is the diagram I will start with, and I will try to draw 90 degrees on that. So here is the line of action of B. So So this time, instead of line of this is the line of action of A. Now this time I'm going to use line of action of B. Action of B, and from the tip of this, I'm going to draw 90 degrees on there. Sometimes the B was up to here, but I had to extend it. It might hit some extended. So this thing will be projection of, this is what we'll call it, projection of A on B, and you can clearly see that this is not the same as that. Okay, so projection of A on B is different than projection of B on A. Okay, these projections turn out to be positive numbers because they are in the same direction as the original vectors. So this projection is positive and this projection is positive. Both are positive. Sometimes projections will be negative. Okay, and you can see from just I'm going to erase this and then clean up, and I'll show you what the formula for projection will be. Okay, so this time we draw the same diagram and we want to go get a formula for this projection of B on A. So this is the common point. You draw both the vectors from the common point. So this is a common point. And from the tip of B, we drop in 90 degrees in the direction of A. This time it falls on the direction of A. So we want to know this related with the length of that. And we're going to use symbol B for the magnitude B. So sometimes if I have a magnitude of B, so its magnitude will be written like this, or something, simply B without the arrow for magnitude. So this is the symbols for that represent magnitude. So you can see from this triangle PB, and let's call it little x, in this triangle PBX, P to X, that distance will simply be this distance times cosine theta. So this will simply be B times, let's make it more traditional way of writing it, B cosine theta. Now, if I were to do the other way and do the projection of, so projection of A on B, here you can see that this distance, this will be the vector A. So this from here to here will be A, and you can rotate in your mind this right angle triangle. This again is the base, so this just will be equal to A cosine theta. So one way to remember is, so projection of whatever that is the length of the projection will be proportional to the vector you're projecting. You're projecting B here, so it's going to be the length of B. You're projecting A here, so you're going to be the length of A. That's the way to remember it. Another thing to notice is this angle's cosine theta. Cosine theta, if you plot versus theta, it starts with 1, and at 90 degrees it goes to 0. So, and this 180 degrees is minus 1. So if the angle between A and B was more than 180, more than 90 degrees, then the projection will be negative. So if the situation was like this, you can see that if how do you make 90 degrees? Well, you have to get the B backward. You have to extend the B backward, and then you can get the projection of A on B. And so this will be a negative projection because the angle theta is more than 90 degrees. It will still be A, This is theta. So A cosine theta, because I'm projecting A on B. So this is the projection of A on B. But this number will be negative now. And another thing to notice is if I have A and B completely 90 degree, then cosine theta is 0. So if I have A this way and the B is 90 degrees to it, but there's nothing it can project on. So if I project tip right there, I get a 0 projection of A on B. How about if I project from B on A? It's the same as equal to 0 is equal to projection of B on A. So we say the projection actually carries a very important information. How much of this vector is along other direction, the direction of the other vector. Okay, and we're going to use projection to define one more property called how do you multiply two vectors. There are two ways to multiply two vectors, and we're going to do that next. Okay, so next concept we want to be very clear about is scalar multiplication. Often in physics there is quite a lot of application of this. For instance, work of a constant force F, when displacement of that object is d. When you want to find the work, then you have what is called dot product or scalar multiplier. So you take this thing and multiply this displacement, and you get a scalar multiplication. For instance, you have some luggage, you're pulling in that direction, F, and the luggage was pulled all the way here, and the same force, this force was acting all this time, and this was the displacement d. Then a scalar multiplication of this with this is the work. So the work equals to F, and the way we denote this multiplication, put a dot, and that's why it's called a dot product. So it's a dot product. So what is the rule for, what's the value for this? What's the formula for something like this? Well, it's a projection of one vector on another, and the multiplication of the the magnitude of the other vector. So this will be with a projection of, say, F on D, line X on D, times the magnitude of D. So this will be something to do with how much of the force is acting in that direction. So from the previous formula, you will say, hey, let me see what the, so there are two vectors here, and they're all different places. I need to draw them the same, so the D is that way, and this is the common point P, and I draw this force F. Now they don't have to be the same type of quantity, unlike the adding vectors. When you're adding vectors, they have to be the same quantity. Multiplying, they don't have to be the same quantity. So if the angle here is theta, then take magnitude of this, and from there I can construct this thing, right? So the projection will be this, and that just F cosine theta, writing like that, and times D, and then this, well, we could have done the other way, because this is the same as D dot F. So I could have projected D on F and then multiplied with F. I'll get exactly same thing. I'll get a D cosine theta F. So you can write this the dot product of two vectors using a combined same formula. So dot product will be like take a vector A and vector B and cosine theta. So this is just a number. So once again you can see that depending on theta it can be positive or negative. So is a positive if theta is less than 0 or less than 90 degrees, is actually 0, meaning if theta equals 90 degrees. If the force was perpendicular to this displacement, this force will not do any work. So suppose there was a force F prime which was 90 degrees to the displacement, then this force is not doing any work. That's what the 0 is. And it's going to be negative if theta is less than 90 degrees. So like if there was a force which was opposite to the direction of its displacement, it's going to do negative work. It's not going to do positive work. It's going to do negative work. So this is a common formula, but you can see it's very important formula for detecting whether vectors are perpendicular or not. So if you say two vectors are perpendicular, how do I write it in a formula way? The formula way would be their scalar multiplication will be 0. So if two vectors have their scalar multiplication 0, you can be very sure that they are perpendicular to each other. Sometimes called they're normal to each other. Okay, the final quantity to actually learn is called vector product, or sometimes called cross product or cross product. The reason it's called cross product is you represent them. You represent this product instead of dot. You represent with a cross. Now, with the dot product, you got a number. You just got a scalar number. You got a positive, a negative, or 0 as an answer when you do a scalar product. Vector product, you instead get another vector. Is another vector, say C. Okay, so which means I need to say, hey, when I do this, what's going to be this guy's magnitude? So what will the magnitude will be like, and what the direction of this vector will be like. Remember that I need to give you both of these things in order for this because this is a vector. Over here I didn't need to give you the magnitude and direction, things like that. There's only one thing, it's a scalar. Here I need to give you both things. So magnitude is going to be it will be the area of the parallelogram. If you put these guys, like you have A this way and B that way, so this is A and this is B, and this is the plane. Let me draw it a little bit better. Okay, so I draw it so the whole thing looks like a three-dimensional perspective, because you do need a three-dimensional perspective when you're talking about vector product. Okay, all right, so you draw this and it will form in some plane. You don't need, doesn't need to be XY plane, but just for the sake of concreteness, I put X and Y there. You don't need that, but you have some plane in which these vectors will fall. So suppose B was over here. Well, I will just bring it over here and write from the common point. So this is their common point P. Common point. And I draw A this way and B that way. So I will make the plane that way. Whichever it is, wherever the plane is, it can be in space, whichever direction it is. But when you draw two vectors, it's going to be in a plane. So I'm going to draw from the common point and it will form a plane. You can just convince yourself of that fact. Okay, so when you draw this in one plane, then there will be let's complete this parallelogram. So this is this A over here. this is B over here, A over here, and this one will be B over here. So when you complete this parallelogram where two vectors will form, having drawn from the common point, so there is an area of this thing. This area of this parallelogram is a number, is a positive number, and that is the magnitude. So magnitude is this. So now if one side is A, another side is B, and this angle is theta, then it will be, magnitude will be equal to A, formula for parallelogram will be sine theta. Over there was cosine theta, this side will be sine theta. And this is not a magnitude of a vector, it's just the formula is because of projection. Over here is actually magnitude of the area that's formed by the two vectors. To get the direction, we use what is called a right-hand rule. So the direction will be perpendicular to this plane. So it will be either it's going to be this direction, or it's going to be this direction. It's going to be 90 degrees to this plane. Okay. So in here, if it's xy, it's going to be either positive z direction or negative z direction. So if you somehow define your xy to be the plane of A and B, then it's going to be in the z direction or in the opposite of the z direction. And the question is, which is the right direction? So we use right-hand rule. There are many ways to do the right-hand rule. So here, in this particular way, if you do it sweep from A to B, the thumb will point to the right. And some people don't like that because it's just too much work. Some people say, okay, I'm going to put the A along the thumb and B along any of my fingers. Then, so it's like this over here, and the direction in my thumb points is the direction direction along this. So this is the plane, and the direction my palm is facing. That's the direction is going to coming out. So the direction of this will be use right-hand rule. And make sure that perpendicular to the plane in which A and B can be placed. So the plane that A and B, the vectors A and B are together forming, once you draw from the common point, so you're drawing from the common point, and once they're forming, and then the direction is very easy to get, because when you got already figured out the plane, right, in which they are, all you have to do is going to do right-hand rule at that point. So I find students really, they don't look for the plane and they just keep doing right-hand and they get totally confused. So my advice to you is just first find the plane and then do the right-hand. It's going to be very easy for you. Okay, so that's the way you do it. And then let me do some problems now as applications. Okay, so the application of scalar product, we already discussed one application. So this is the work by this force in the displacement of this box, say luggage or something like that. You're pulling the luggage. The application of vector product in physics is also very common, you know. So one of the things, you might not have seen it this way, but the torque is also a vector, which is it's given as from some common point r. It's given an r cross f. So I'm going to illustrate. Say you have some kind of bar, and the gravity acts over here. And so let's call this force F. and let's see, pivot point is there, and so where this is where the force is acting, and this is the pivot point. So this vector from here to here, that's the vector called r. So you remember when we define this, we actually, when we define this, we did something, draw these vectors from the common point. So I need to draw this vector from there. It's not over there. So I'm going to redraw it. So this is my r from the common point P, and I'm going to move this to act down here. And now it says what the angle I need. This is the angle theta. And so this will have a magnitude, will be area of this parallelogram, right? And that just r times f times sine theta. And you can convince yourself that's the area of the parallelogram. Okay. What's the direction? Well, we already know this is in this plane, so it's going to be, you will be either this way, or r is going to be back that way. These are 90 degrees to that plane. Okay, so which way it is? So we use a right hand rule, go from r to f, and it seems like this way. So this is the correct direction. So this is not the direction. So this is the direction. Use right hand rule. Once you find the plane, use r, go towards the f, and it's going to thumb will point in the direction, and it's very easy to figure out. Because you're just picking between two opposite directions. So that's the torque. And let's do some. Okay, so this is a very generic problem, and I'll take some problems from Kleppner and Kolenko. I like their problems very much. So here is a nice problem, and I forgot to mention that in the dot product, you may recall that A and B perpendicular if A dot B turns out to be 0, right? Because A dot B is A B magnitudes cosine theta. So if theta is 90 degrees, then this will be 0, right? Okay, so it seems like we need to you can also, we need to be able to somehow get this. So another over here, you can see I can use dot product of A with A to get A cosine 0 degrees, that's 1, and so this is A square. So magnitude square is also dot product. This is also very important relation. So what's given here is magnitude of A minus B is equal to magnitude of A plus B. So which means if I square both sides, this is just numbers. So A minus B square must equal to A plus B square. And on each side, we can just try to expand it, because I'm trying to figure out where I'm going to get A dot B. So if this is in magnitude, I need to be able to get to the dot product. So when you do this, this side should just become A minus B is some vector. It's going to be dotted into itself. The important step. If you didn't get it, then you can just think about it yourself. Another way to think about it is, let's C is equal to A minus B. So C magnitude is equal to, if you square it, then it will be C dot C, and then I just put A minus B dot A minus B. That's what I did over here, right? And on this side, I do the exactly same thing of A plus B dot A plus B. Now I'm going to expand this. By the distributive property, you are going to get this with that, this with that, this with that, this with that. So I'm going to get A dot A minus A dot B when I did this guy. Then I'm going to get minus B dot A minus plus B dot B. And on the right side, it's going to be A dot A, just working with that, A dot B plus B dot A plus B dot B. Now this guy we're going to cancel with that guy. This guy will cancel with that guy. And we know that from the definition of A dot B, we already know that this is A B cosine theta, and I can just, these are pure numbers, so this is same as B A cosine theta. So this is same as B dot A. So A dot B is same as B dot A. This is not the same thing in the cross product. A cross B is not equal to B cross A. Actually, A cross B is equal to minus of B cross A, because the direction will have to flip. So it's different than what happens in dot product. So all of this is going to be, send this everything, I'm going to get 4 times A dot B equal to 0. That means A dot B equal to 0. That means A and B are perpendicular. Okay, so here is a problem that you can do almost the same way as I showed you how to do this problem. Here you would be able to write C in terms of A and B and D in terms of A and B. So the hint is write C and D in terms of A and B, then solve A in terms of C and D and B in terms of C and D, and then use this and use that, and that will be the answer. Okay, so but it's important for you to carry and have this good for your practice. So I'm going to stop there. You can check out my website. You know, this is a long big textbook. It's freely available, and there are a lot more examples there. So what's the next coming up? Well, we did graphical things, and we're going to do algebraic things. So just to recap, well, today what we did was vector as magnitude and direction, and we didn't do any components or anything. Didn't actually use any Cartesian coordinates, etc. to speak of. Okay, so the vectors are just you can represent my arrows, etc. And you can move them around as long as they maintain the direction. You can multiply with a scalar. If you multiply with a positive, it just keeps its direction. You can, if you multiply with a negative, it reverses direction. Multiply by 0, of course, you get a 0 vector. And vectors have a very special way you can add. They add according to what is called law of the parallelogram we illustrated earlier. Some of the other things that go with vectors that you must remember, one is a projection of a vector on the line of the action of another vector. Okay, that's very important concept that got used in scalar product, and then we had a vector product where we used actually a parallelogram that was formed by two vectors. We use the area of that parallelogram to define the magnitude of this a new vector. We are calling it cross product vector or vector product vector. Okay, and the direction was used in relation to the plane that A and B had formed. It was perpendicular to that plane. It's going to be either pointing one way above that plane or pointing another way, and we use right-hand rule to find out which way it's pointed. Okay, that recaps everything. I'll see you in the next video. Okay, bye.